All right, so we're in part 2 of section 13.8. And we're going to talk about absolute extrema. Now on Friday we talked about relative extrema, and we decided that our relative extrema were going to be at critical points where our first partials were each equal to 0. And we came up with our second partials test to tell if we had a maximum, a minimum, or a saddle point. The absolute extrema, let's figure out, let's think back to when we worked with extreme values in single variable calculus. When we were looking for the absolute maximum or absolute minimum, what was different than finding a relative maximum or minimum? What do we have to take into account? We remember? If when we were working with extrema in single variable calculus, and rather than looking just for critical points, if we were looking for an absolute extreme value on a particular interval, what do we always have to take into account? Saddle points. So we need to think about the critical points. But if we're looking for an absolute extreme value, if we're just in the plane, and we have some function like so, and we want the absolute maximum and absolute minimum on the interval a to b, we had to look at our critical points, but what else do we have to look at when we're looking for our absolute extreme values? We have to think about the endpoints of our interval, because our function can take an absolute maximum or minimum on the endpoints as well. So it has a relative minimum here, but it has an absolute, our absolute maximum is going to be here. It has a relative maximum here, but our absolute maximum is going to be here at our endpoint, even though that's not necessarily a critical point. So we have to do a similar thing with multivariable functions, except our endpoints, rather than points, are going to be functions. So we have boundary functions that we have to examine. And that's what makes absolute extrema a little more work intensive with multivariable functions. So the mean value theorem tells us that that if f attains a maximum value or a minimum value in some closed bounded region. So if we have a closed bounded region, closed means it contains its endpoints, and bounded means it's finite. We're going to have a maximum value or a minimum value. And for our functions, after what we just talked about, our maximum or minimum, the absolute maximum or minimum, will be at a critical point or at the boundary of the region. So finding critical points is what we did on Friday. So we have to figure out how we're going to deal with the boundary of the region. So for all of these, we're dealing with our function on some closed bounded region. So our steps, we have some steps that we have to follow to find our absolute extrema. Our first step is we find the values of f at the critical points of the region. So this is what we did on Friday. We find our critical points, and we have to make sure when we find our critical points, because we have a bounded region, that our critical points that we're finding are inside our region. If we find a critical point outside our region, we don't have to worry about it. So if we were looking for, going back to our single variable example, if we're looking for the absolute maximum minimum in this interval, and we come up with a critical point here, well, it's outside of our region, so we don't have to worry about it. Same thing here. We find the critical points and make sure they're in our region, the region that we're interested in. Our second step is find the extreme values of f on the boundaries. So we have to look at the boundary of our region. On the boundary, finding the extreme value of our function may involve taking a derivative of a single variable function and setting it equal to 0, and finding the critical points of a single variable function on the boundary. That's usually the way it works. Is on the boundary we make some substitutions from the conditions of our boundary and turn our function into a single variable function along the boundary. Finding the extreme values on that boundary involve using tools that we already know. And finally, the way we pick is, so we have values of f at the critical points in the region. We have the extreme values on the boundary. The largest is going to be the absolute maximum. The smallest is going to be the absolute minimum. And we're talking about on our particular region. So these are the three steps that we always have to follow if we're looking for absolute maximum minimum. We have to find our critical points. We have to examine the boundary, find the maximum and minimum, find the values of our functions there. The largest value of any of those points is going to be our absolute maximum. The smallest is our absolute minimum. So this is all stuff we know how to do. So what we're going to do next is go through a couple of examples. The examples, because of this condition, they take a little bit of work. So any questions before we go on? All right, so let's look at a couple of examples. Our first one, we want to find the extreme value of f of xy equals 2x minus y squared. On the region, and we're going to define a region in the xy plane with some points. So our region R is between the points 2, 0, 0, 1, and 1, 2. So we're looking at this function, and this is the boundary, this is the region that we're interested in this function. This is the region in the xy plane. So if I make a quick sketch of this region, and this can be helpful when you look at this. So we're here at the point 0, 1, and we go up to the point 1, 2, and then back down here to 2, 0. So our region is this triangle in the xy plane. So our function is above the plane of our board here. Let's make some kind of surface up above the plane here, and we're only interested in the extreme values that are within this triangle. So our first step, we need to find the critical points. And this is where we use our partial derivatives. So we take our partial with respect to x, gives us 4. I'm not going to go through the steps, but we get 4 times 2x minus y. Partial with respect to y is negative 2 times 2x minus y. And our critical points are where those equal 0. So f sub x equals f sub y equals 0. If I solve those simultaneously, this gives me y equals 2x. So when I set both of these equal to 0, set them equal to each other, I get y equals 2x. So inside the region, this tells me inside the region, our critical points are on the line y equals 2x. So now what I'm going to do is say if y equals 2x, plug that back into my function, plug 2x in for y. If y equals 2x, that tells me that f of xy equals 0. So I'm plugging 2x in for y in my original function. So along the line y equals 2x, f of xy equals 0. So there's one point or set of points that we're interested in. Along the line y equals 2x, our function is 0. So there's our first step. Now for our second step, we have a fair amount of work to do, because this boundary is a line, this boundary is a line, this boundary is a line. So we have to look at the extreme values of f on 3 different lines. So our boundaries are lines, so we have to examine each line for extreme values of f. So let's take a look at the boundaries. Between the points 0, 1 and 2, 0, the equation for the line there is y equals minus 1/2 x plus 1. So that's the equation of this line. Now I'm going to substitute this in for y in my function. So on this boundary, f of xy, when I make that substitution, I get, after some simplification, 5/2 x minus 1 squared. So on the boundary, this is my function. I need the extreme values of the function on this boundary. And we're also bounded by x between 0 and 2 and y between 0 and 1. F is a minimum between 0 and 2. F is a minimum when x is 0. So I'm just looking at this equation, looking at my values of x and my values of x here, and saying, well, when x is 0, this is going to be the smallest. F is a minimum when x is 0, and f of 0, 1. When x is 0, y is 1. F of 0, 1 equals 1. So there's an extreme value on that particular boundary. F is a maximum when x equals 2. And f of 2, 0, just plugging back into my original function, f of 2, 0 is 16. So this isn't going to be one of our absolute max or min because it's bigger than the ones we found here. But this one could be. This one could be a maximum. So this is the biggest value we found here, is at f as at the point 2, 0. So that's just for one boundary. We have to do the same thing for each of the 3 boundary lines. So we found one set of points that could be our minimum on the line y equals 2x in the interior. And we found one point that could be our maximum at the point 2, 0, which gives us a function value of 16. So let's look at our next boundary. Questions before we move on? Okay. So we'll pick a couple more points. Between the points 0, 1 and 1, 2, our equation for that line, y equals x plus 1. Substitute this y into my original function and simplify, and I get f of xy equals x minus 1 squared. And we're looking between x equals 0 and x equals 1. So f is a maximum on this line. F is a maximum when x equals 0. That gives us our biggest value here. So f of 0, 1 is 1. We looked at that one before. And f is a minimum when x equals 1. And substitute that point, 1, 2. F of 1, 2 is 0. So there's another minimum. This is the same as the minimum we found on the interior on the line y equals 2x. So this could be a point that we're interested in. So now we've looked at 2 of our boundaries. We've looked at the interior and 2 boundaries. We need to look at one more boundary, and then we can decide where our absolute max and absolute min are. So between the point 1, 2 and 2, 0, the equation for that line is y equals minus 2x plus 4. Substitute that into my original function, and I get f of xy equals 4x minus 4 squared. Substitute this in and simplify. F is a maximum. And we're looking at x between 1 and 2. F is a maximum when x equals 2. And f of 2, 0 equals 16. F is a minimum when x equals 1. And f of 1, 2, we've already found that, equals 0. So here we've decided that the minimum value that f takes on the region is 0, and that happens at a few places. And the maximum value of f is 16. So our absolute maximum and minimum, after all this work, absolute maximum is at the point 2, 0. And f of 2, 0 is 16. So our maximum value is 16. Absolute minimum at 1, 2, and along the line y equals 2x, and f equals 0. So this one, the analysis is pretty straightforward, but our boundaries were lines. If our boundaries are more complicated, examining the boundaries for maximum and minimum can be much more difficult. Usually it's going to involve on your boundary, if you have some complicated function as your boundary, you're setting the first derivative, you're taking your first derivative of the function you end up with on your boundary, setting that equal to 0 to find your maximum minimum value on that boundary. So tools that you've used in calculus before. Let's take a look at what this function looks like on this region. I made a little graph, so let me get to that. Oops, that's not what I wanted. I wanted this one. So there's our surface. And our region here in the XY plane, if I lay it down on the side, there's our triangle. Here's our point where we found the maximum value of our function, and our minimum values are down here, and the line y equals 2x would be along. Let's see, how did we end up with this? Minimum along y equals 2x. So here's our line y equals 2x down here on the xy plane where f is 0. And then our maximum is up here at the point 2, 0 where f is 16. And the line y equals 2x would be along here where our function is 0. So this is our function on our region. And this was a nice boundary and a nice function. Any questions? So these problems typically not difficult. Generally they involve a fair amount of computation because of the work you have to do with the boundaries. Okay? Homework. There you go.